All right, last section in chapter 8, improper integrals. Improper integrals simply refer to integrals that have infinity as a bound. Clearly you can't evaluate infinity as a bound, so what do? And what you're going to see is kind of a culmination of a few of the previous sections, as well as specifically using L'Hopital's rule when we evaluate the limit at the end. But here we go. A definition of a definite integral requires that the interval AB be finite. Furthermore, the fundamental theorem of calculus, by which you have been evaluating definite integrals, requires that f be continuous on AB. In this section, you will study a procedure for evaluating integrals that do not satisfy these requirements, usually because either one or both of the limits of integration are infinite, or because f has a finite number of infinite discontinuities in the interval. Think about that. Finite number of infinite discontinuities. Integrals that possess either property are improper integrals. Note that the function f is said to have finite discontinuity, infinite discontinuity at c, when it approaches infinity. That's all this is saying. But if you approach that point and the y value is actually approaching infinity or negative infinity, then it's considered an infinite limit, or infinite discontinuity. Discontinuity, because clearly we can't actually have a point there. So here are our circumstances. If our upper bound happens to be infinity, then what we're going to do is replace the integral with the limit as b approaches infinity and put b in its place. If the lower bound approaches negative infinity, then we're going to do the same, except let a approach negative infinity and put a in its place. And if by chance both of them are positive and negative infinity, then we're going to figure out a spot in between to separate it and then do a combination of the first two rules. Here's what I mean. I can't evaluate this integral, so as is. So what I'm going to do is replace it with the limit as b approaches infinity. We always use b as the upper bound. As b approaches infinity, from 0 to b, of e to the negative x dx. I haven't done anything to the integral itself. I'm going to evaluate the integral as is. This is e to the u du, but only once there is a negative here and a negative here. I'm not going to write e to the u du. I shouldn't have done this anyway. I'm just going to write the answer, which is e to the negative x. From 0 to b. I can plug in b. And I can plug in 0. Okay, so what I just did was evaluate this at b and at 0. The one on the right can actually be evaluated for a specific number. The one on the left cannot. But I am going to clean up what I have in front of me. A negative exponent means that it drops to the denominator. And e to the 0 would be 1. With a negative in front is negative 1. With a negative in front of that is positive 1. So now my job is just to evaluate this final answer. If my denominator is growing such that the exponent is infinity, then the entire denominator is infinity. 1 over infinity is 0. So the final answer here is 1. 0 plus 1 is 1. I probably should have written this as 0 plus 1 equals 1. Alright, I couldn't evaluate it as is with the infinity, so this is the correct way to do that. Alright, what's the problem here? It's not an infinite limit, but I have a discontinuity at 0, right? If 0 was in my denominator, then I would have an indeterminate form. So I'm going to rewrite this as the limit as a approaches 0 of, and I'm going to make this more integrable, x to the negative 1/3 dx. I'm going to go ahead and integrate that. from A to 1. And then I'm going to rewrite my limit portion and evaluate it for 1 minus A. You're going to see that I write this very differently so many times. Like before, I wrote with parentheses. I probably should have put a bracket around all of this. I apologize about that. So evaluate what you can and leave alone what you can't evaluate. 3/2 times 1 to the power of 2/3 is 3/2. And now what would happen if I plugged in 0 where A currently is? If 0 was here, then 0 to the 2/3 is still 0. This whole portion would be 0. 3/2 times 0 is still 0. So I'm taking 3/2 minus 0, which is 3/2. Okay, I wouldn't be able to plug in 0 as is when I integrated it, or right from the beginning. So this is the correct way to write it, even though I probably could have figured it out. All right, keep moving. What's the problem here? Why is this not written correctly? What do I need to do to change that? So, if you look carefully, you would hopefully recognize that there is a discontinuity between the interval -2 or -1 and 2 at 0. You can't have 0 in the denominator. So we need to break this up where there is that discontinuity. This kind of reminds me of the difference between texting and writing a formal paper. You could probably figure out the answers to a lot of these without going through this whole process, but is it written formally? It'd be like you could get your point across if you just texted in shorthand, the way that you normally would text your friends. But would that be acceptable as a formal paper? And the answer would be no. You'd have to have the correct punctuation and the correct capitals and things like that. And that's basically what we're addressing here. Do you notice any other problems? Well, when I integrate this, or this particular graph cannot exist at 0. I have a problem at 0 because that would be incalculable, it would be indeterminate. So I'm going to rewrite this as the limit as my upper bound approaches 0. So not actually at 0, but as we approach 0. And this one as the lower bound approaches 0. I'm not going to write it. I wish I had already written it, but the 1 over x cubed is really x to the -3. So remember that as we're integrating. This becomes x to the -2 over -2. And so does this one. Alright, this is going to be a little bit longer, so I'm going to stretch it out over here. Remember, a negative exponent means that it drops to the bottom. So this becomes 1 over -2b squared minus 1 over -2 times -1 squared. This becomes 1 over -2 times 2 squared, and 1 over -2 times a squared. Evaluate what you can and leave alone what you can't. Oops. That negative doesn't matter if you put it in the top, the middle, or the bottom. This becomes 1. This becomes -2. This becomes positive. Two, 4, -8. This becomes positive 1/2a squared. All right, if b approaches 0, remember it's approaching 0. It's not actually 0. So -1 divided by 0, or something really close to 0, would be infinity. In fact, it would be a negative infinity. And I'm going to add 1/2 to it. And then I'm going to subtract 1/8. And then I'm going to add 1/2 times, this is going to be a positive infinity. So I'm going to actually double check this one, because I ended up with 2 different infinities, and I'm not supposed to have that. But instead of wasting time now, I'll come back to you with the correct answer for that. Infinity is a problem here. I'm going to rewrite that as the limit as b approaches infinity of the integral from 1 to b of 1/x natural log of x. We've seen this a couple times where this has been u and the 1/x has been your du. So this is 1/u du. Okay, I'm not going to write 1/u du because then I'd have to change the bounds. But it becomes the limit as b approaches infinity of, well, what's the integral of 1/u du of the natural log of u? Natural log of the natural log of b minus the natural log of the natural log of 1. This could get messy too, because the natural log of 1 is 0. And you can't calculate the natural log of 0, but can we figure out what it would approach? If this was just slightly off of 0, like 0.00000001 or something like that, then we would be asking ourselves, e to what power would be that really, really, really tiny number? And this would mean to me a negative infinity. Because if e was raised to a negative number, it means that it would be growing in the denominator. And 0 would only be able to be approached if we were growing in the denominator. So if this is negative infinity, with a plus or a minus in front makes that positive infinity, and then this is infinity, right? Natural log of infinity would be infinity, and the natural log of infinity would be another infinity, and infinity plus an infinity would be an infinity. So my theoretical guess to this would be infinity, even though I can't evaluate that number. It just supports that we're approaching infinity here. Whew, a lot of theoretical. We're almost done with chapter 8. Last one. I see an algebraic and a transcendental, so what I'm going to do is, when I integrate, I'm going to use integration by parts, and I'm going to use my tabular method with the Lie. And I'm actually going to do that first to get it out of the way. We start with a positive x squared e to the negative x. I'm just going to quickly move down till I get to my 0. These alternate, and these are just going to go back and forth, alternate as well. Okay? Which means that when I integrate, this is going to be positive x squared times that, so negative x squared e to the negative x, negative 2x e to the negative x, negative 2 e to the negative x plus c. Alright, my problem is going to be just the infinity. 0 won't be a problem because that becomes 0 and this will become 1. That's not an issue. So the limit as my upper bound approaches infinity when I integrate it, which I already did, it's going to become negative x squared e to the negative x minus 2x e to the negative x minus 2 e to the negative x plus c. But it's not a plus c because it's a definite integral. I'm going to rewrite this also. Instead of having negative exponents, I'm going to write it the way that it should be written. I'm going to go even further, and since all those denominators are the same, I'm going to simplify it to one denominator. All right. If I plug in b, and if I plug in 0, then what can I do? I can evaluate the right term here. I can't evaluate the left just yet. Zero minus 2 is negative 2, and this denominator is 1. So this is negative 2 over 1, but a negative in front is a positive 2. All right. Now let's talk about the theory. If infinity is plugged in for b, then my numerator is approaching negative infinity, and my denominator is approaching positive infinity. But they're different infinities, and I can't calculate them as is. So in order to calculate them, I'm going to apply L'Hopital's rule, and I get negative 2b minus 2 over e to the b. Can I plug in infinity now? Well, that's still going to be negative infinity over infinity. And do L'Hopital's rule again. I get negative 2, and really I should have written the limit as b approaches infinity. The limit as b approaches infinity. At this point, I can calculate it. I get negative 2, which is a static numerator, and I have a denominator that's growing toward infinity. This is bottom heavy, so this whole thing is approaching 0. That means that my limit is 0 plus 2, which is 2. Okay? Make that question. If you have any questions on this, again, I'm going to come back and address the one that I skipped out on and maybe come up with a better response to this one right here. But for right now, we're just going to close it as is. Your test would most likely resemble some of the others. If you have any questions, you know